Hello, this is the 11th review session for CS 333. That's CS 333. The topic of this review session is linked lists. Now, up until this point, we've discussed a number of things, one of them being arrays. And now the key benefit of arrays is, let's say I know I'm going to have 10 rooms in the very beginning. I know I'm going to have 10 items in my array. What I do from that point is I say, well, I allocate these 10 blocks of memory, and I can access them as I wish. If I want to access the first, I use an index of 0. I want to access the last of those 10, I use an index of 9. The key benefit being I can access any random room in any position at any time. But I can't change the size. Once I create 10 rooms, that's all I can ever store. And we've discussed some ways around that. We discussed some ways around that. And we looked at that in the previous example. Now, this is a continuation of review session 9, when we looked at abstracting away that room collection, where we looked at that dynamic array, something you saw in the earlier arrays assignment. What I do is I say, you know what? I'm going to allocate room for 100 rooms. I'm not going to use all of them though. I'm going to allocate space for 100, but I'm going to start by storing none. Then every time I add a room, I'm going to increment this auxiliary counter. This being the total amount of space I have, and this being the actual number of slots I've used. Now that has the benefit of allowing me to resize my array. And by resize, I really mean use more or less of the room I've allotted. I'm not really resizing. Linked lists are a different data structure. Instead of saying I'm going to allocate 100 spaces, I'm going to say I'm going to work entirely with pointers. I'm going to start with nothing. I'm going to have one pointer that points to null, points nowhere. Then when I add that first item, it's going to point to a block, to a node. Then, if I want to add a second node, I go to that first node and I point it to the second. If I want to add a third item, I go to that first node, I go to the second, and then I have the second point to the third. And I continue like that, and the chain can go on forever. The benefit being I can add and remove fairly quickly. Well, not fairly quickly, but I can add and remove without any sort of restriction on the amount of space I allocate beforehand. I don't allocate any space beforehand. I allocate or deallocate on the fly as I need it. But I lose the ability to access a random node. For example, if I have a linked list of 100 nodes, to access the 90th node, I must start at the first and move forward until I reach the 90th node every time. I can't use array indices, none of that exists. It's start at the beginning and move to the 90th. And there are variations on a linked list around this, a doubly linked list and a number of things. But for this discussion, we will focus on a singly linked list with a pointer to the head of my list, the head pointer that points to the head of my list, the first node, the beginning. And each node will point to one other node, the next one in the sequence. And that's the variation we were discussing tonight. But before we move into that, we're going to revisit the array example, the one we left off with in the previous review session 9. So I had this array of rooms. I kept track of the size, the number of rooms I'd actually stored. And I had my constructor. I had a function to add a room. I had a function to sort. I had a function that told me the current size. I had the array subscript operator, these brackets. I had a display function. And then I had the stream insertion operator that simply said, hey, I'm a wrapper for the display function. And then all I did in update room at that point was allocate this collection, prompt the user for each of these rooms, invoke the add function, invoke the sort function, and then after a little bit switch to invoking the stream insertion operator, the cout operator, if you will. And that's where we left off. Now, if you'd like a more detailed review of this, go to review session 9 where I discuss this in further detail. Now, linked list. Now, for linked lists, sorting a linked list is a little bit, sorting a linked list and implementing the array subscript operator are something we don't have time to discuss tonight. Sorting a linked list is an interesting topic, but something that belongs more in an algorithms course. For example, CS 361. Implementing the array subscript operator for a linked list, while not complicated, is unnecessary for this discussion. And if you are interested, we can discuss it during my office hours, or you can wait until CS 330 next semester and I'll be discussing it as one of my first examples at the beginning of this upcoming spring 2016 semester in CS 330. Now, that was example 1, which was a copy of the last one from review session 9. Let's go ahead and open up update room and these two room collections here. Now, update room is the driver. That hasn't changed too much. If I scroll through update room, we'll see still allocating that collection, still prompting the user for each room. I've commented out the sort function because we will not be implementing a sort function for this linked list. We'll leave that for an exercise in a later course, 330 or 361. And I'm still outputting. Other than commenting out that sort line, my main function is the same. But when I jump into room collection, I've entirely changed my data structure. It is now a linked list. And now this is very similar to that the hand class in the linked list assignment. I have a node that I've specialized for this specific application. In the lecture notes, you see a version of a linked list that uses template functions, template types, and all of that. For this, I'm not doing a generalized linked list. I am doing a linked list specialized for this room collection. Now in practice, I would generalize this, but for this discussion and for the assignment, we are specializing it to that case. Now, nodes are a very, very simple struct. They contain two attributes. The piece of data I want to store, in this case, a room, and a pointer to the next node. Very important, a pointer to the next node. And for ease of implementation, ease of use, I have implemented a constructor here that takes the piece of data I want to store and constructs the node around it immediately. And takes this next pointer and initializes to null. So it takes whatever room I pass in as D, stores that in data, and sets next to null. That's what we're going to see in a moment when we look at the definition of this. I replaced the allocation of the array with this head pointer, the pointer to the head of my list. And then actual size, don't need it. I don't need to keep track of the actual size for the linked list. What this allows me to do is track the number of nodes in my linked list, which is very useful. It's very useful to know the size of my linked list without having to traverse it each time. So I'm simply incrementing and decrementing this counter, incrementing when I add a node. And we're not removing nodes in this example, but if I were to remove a node, I would decrement this counter. So a pointer, linked list. Create this node, create this linked list element, this node. Allocate a pointer to the head that is the beginning of that list. And if you want to keep track of the size, if you want to keep track of the size, throw a counter in there to keep track of the size. If you don't want to keep track of the size, don't include the counter. I still have a default constructor. I still have an add function, and you'll note that it still takes a room. We are not going to be implementing the sort function. Once again, this might be something we look at in 330 next semester. But if you'd like to discuss further, we can do so during my office hours. A function that returns the size of my room collection, something I'm not concerned about. Now the array subscript operator, something we could implement, but for sake of brevity, we will not be discussing it tonight. But it is something we'll look at the beginning of CS 330 next semester. And then the same stream insertion operator for this room collection. Now, this is where the fun begins. This is what normally gets most students. Room collection, scope, node, scope, node. So, I have a room collection class. This node struct exists only within the room collection class. So this node struct exists within the scope of room collection. I am implementing a constructor within the scope of this node struct, which exists within the scope of room collection. My node constructor exists within my node structure, which exists within my room collection. So I have two levels of scope there. First, I need to go to the room collection scope. Then I need to go into the node structure scope. And then I need to write the constructor. And using an initializer list, an initialization list, I take that piece of data D I pass in, initialize my room, I take my next pointer and initialize it to null pointer. Once again, with an initialization list. Then I jump down. Look at my room collection. I need to initialize the head pointer to null pointer. At this point, my linked list is of cardinality that is size 0. There's nothing stored in my list. And now I move on to the add function. When we were working with arrays, we could write it as one line. That's no longer the case with a linked list. And I still left that assertion in here. We'll see that when I'm working with a linked list, I'm working with nodes. So if I want to add something to my linked list, I must first construct a node around that data I want to add. So I'm still passing in the room data I want to add. My second step, once I'm in this function, is to construct a node around that room. Create a new node around that room. That's my first step. Allocate that node, and then I can move forward. Now, with the linked list, I have two special cases. Well, one special case. So 2 cases total. This one special case is if I'm adding the first node, I don't have a list. My head pointer points to null. I have no list with which to work. So adding that very first point is actually the easiest form. What I'm going to do is allocate that new node as I've done here. If I don't have a linked list, if I have not added at least one node, I simply take this new node, and that's the head of my list, and I'm done. Like so. And because I'm working with pointers, these now point to the same block of memory, and I'm good to go. And then I increment the size by 1. I don't do anything else. I reach the end of this function. I've added my first node. Now, let's say I'm adding my second, third, fourth, fifth, or eighth node. Anything other than the first node is the same. I still need to allocate that new node. I still need to take that data I want to add and create a new node around it. If I'm looking, now I need to do something. I want to add this to the end of my list, which means first I must get to the end of my list. I must get to that last node and stop. So I'm going to allocate a pointer to a node. I'm going to have that pointer reference the head of my list, the beginning of that linked list. And then I'm going to traverse the entire list. Start at the beginning of my list, move to the second node. Is the second node my last? No. Okay. Move to the third node. Is my third node the last? Repeat, repeat, repeat. Am I at my last node? Good. If I'm at my last node, it points to null. If I'm at my last node, don't move any further. Stop at exactly at my last node. Once I have reached my last node, stop. Then I'm going to say, I'm in my last node. I'm pointing to it. Within that last node, grab that next pointer. Take that next pointer within my last node and point it to this new node I've just created. So take my last node and connect it to this new node I've just created. And now this new node is at the end of my list. I've now increased the length of my list by 1. I've added a new node, increment the size by 1. And repeat every time I call this add function. And the lecture notes do go into a little bit more detail. So if we scroll down, we'll see that I'm still returning that actual size counter. That hasn't changed. We look at the display function. You'll note I've left the for loop for an array. That's still there, just for reference, commented out, of course. But I still want to output something similar. I still want to output the room number. And you'll note that I have corrected the typo. That is now out as it should be. That output stream, the generalized output stream I'm passing in. Output the room number I. So I've had to declare an integer I because I'm no longer working with array, so I have to declare this integer. Initialize it to 0. First, start to output this line. Increment I by 1 because it's a pre-increment operation, something we saw earlier in the semester. Output that 1, end the line. Then take that current node I'm referencing, grab the room, the data stored within that room data. I now have a room, the parens added for readability. Display that room using the output stream, print a blank line, move to the next node in my list, repeat until I reach the end of my list. You'll note in this earlier loop, I wanted to stop when I reach the last node. In this loop, I want to visit every node. This is what I refer to as the standard linked list while loop. This is the while loop you will write every time you want to traverse an entire linked list. Very similar to that standard array for loop up here. The standard array for loop, the standard linked list while loop, along with an iterator here as well, starting at the beginning of my list. Now, example 3 is the same thing. Now, update room once again hasn't changed. All I've done is clean up room collection.h and .cpp a little bit. You know, in room collection.h, I removed the two functions, the array subscript operator and the sort function, from room collection.h in this third example. I've also added a note. Because I'm working with pointers, I should be writing my own destructor, but that's something we'll discuss in CS 330 next semester as well, in a little bit more detail. For now, let's just focus on creating the linked list and traversing it. Deallocating all that memory is something we can discuss in CS 330 next semester, and it's something you will see in CS 361. But other than removing those two function declarations and this comment here, room collection.h has not changed. Scrolling down, in example 3, you'll note most of room collection add, most of this add function is the same, with one major change. You'll note that I've moved the increment operation down here. Now I looked at this conditional block and I said, you know what? When I add the first node, I'm incrementing that counter by 1. When I add every other node, I'm incrementing the counter by 1. No matter which of these two branches I take, I'm still doing the same operation. Why did I put it in those branches? So if you have code that happens no matter what happens, so if you have code that executes regardless of which branch you take, meaning if you're writing the same code within each part of your conditional block, factor it out. It shouldn't be in that conditional block. If, for example, this counter, if I'm incrementing this counter independent of which path I take, move it outside the conditional block because it always needs to be done, and organize the code to that effect. That's a quick change. Nothing to help you there. A quick review of conditional blocks. You'll note that now my display function, I've commented out that while loop. And I said, you know what? Let's look at something that's similar to what you'd see in the lecture, something that's more closely related to that. So I said, well, I still want to output a number, so I'm still going to allocate this integer I. This line is the same as we saw here. But now, grab that room, and because now I have room, I'm just going to use the stream insertion operator directly. So output the room number, output the room directly. Take my node pointer, grab the room, pass it to my stream insertion operator, and then I'm done. Now, if we look, this is really just my while loop folded into one line. I'm allocating a pointer and starting it at the beginning of my list. I have my loop condition while my iterator is not equal to null, essentially copied and pasted. I have my increment operation, take my iterator and move it to the next node in my list. Last line of my while loop. All I've really done by writing this as a for loop is write it as a for loop. Quite literally. I can write this as the standard linked list while loop, the standard linked list traversal while loop, or the equivalent for loop here. There's no real difference between the two. Now, that was a quick review of linked lists, simply because the lecture notes go into so much detail, and you have that assignment on which to work. If you'd like to discuss linked lists in a little bit more detail, or you'd like to discuss some of the operations over which I skipped, for example, sorting a linked list, implementing the array subscript operator for a linked list, or a couple other things, regardless, I am available during office hours and via email, and we can discuss this in more detail then. along with any other material we've discussed this semester.